I'm going to use this picture to explain the meaning of the derivative. Right, so we have a function. Now this is xy plane and is a UV plane, a codomain plane. And you can imagine U is written nicely if the formula is given, and you can do that. You can work this one out, was one of the test problem, like that. So we have a two real power. So this one is the main object of the Calc 3, which you agree is a two-variable function? Not UV together, just the U part. Would you agree? Two variable and output is one real number. That's how we start the Calc 3. And separately, this one is another object, and then you do that. And directional derivative is about the directional derivative of U, directional derivative of V. That's what the directional derivative is about. But right now what we're looking at is just two real valued functions put together into two things. We've looked at it already a little bit. So the meaning of the derivative is the following. Think about the meaning of f prime of x. Isn't that the rate of change of output value, right? With respect to input value. Slope of a tangent line, slope of the secant line, that's the geometric, visualization of these rates of change, right? That's what I'm about to do here, okay? But the definition you're going to see in the complex number is kind of exactly the same thing as this one, and it's really puzzling. So here's the one example. If I have a W1 and a W2, if you look at quotient of two complex number, remember the definition of derivative involves this quotient. Increment of y divided by increment of x. That's what the slope of a tangent line and secant line is about, right? So it's going to involve exactly like that. If you just write down the same thing and do the same thing for the complex number. Try to give you the meaning of that. So that's a real part. The modulus and the modulus of that, this one behaves nicely like this. Remember that part? If you take the quotient of two complex number, modulus is taking the quotient. But this argument part is slightly different. Do you know what happened to the arguments if you take the quotient of two complex numbers? They're differences, right? 1 minus theta 2. Modulus is the quotient, but the argument is the difference. That's how the De Moivre's theorem works, right? This is the meaning of a quotient of a two complex number. And we're about to write down just formally exactly the same thing you do in a real number and try to figure out what happens. All right, so here is one interpretation of, so this is actually the definition. So f of z minus f of z naught. That will be the difference of output value. Would that be right? Here is going to be a vector, right? And divided by what? How do you calculate the secant line in real input value is minus z0, right? If z and f are real valued function, this will be slope of the secant line, remember? So we took that, just that algebraic formula, and try to give a meaning to this one. Okay? So I'm going to choose one central point right here. Then you see the grid line, and that corner down there is actually this corner. Let's assume that. The coordinate system here, one position, second position, and third position, and fourth position is exactly mapped in here. So do you see, can you locate the central point in here where this one goes? That's a Z0. That one goes exactly the central position there. That's a W0. Does that make sense? Z0 goes W0. So if I choose this value right there, Z, where does that go? On that horizontal line and go in right there in the W. Do you agree? Okay, that's this Fz minus Fzw. So it's going to be W minus W0 and Z minus Z0. Make sense? All right, so how would you represent this complex number W minus W0? What's the best V word that represent this one? Vector, right? So it's a vector. All right. It's the exact picture. W minus W0 is represented by that vector. Directional vector, right? Can you think of the modulus of this one? Things like that? All right. So let's do this one. What was the version again? Quotient of two complex numbers? Modulus is quotiented, right? Does that make sense? Then what about the next one? Difference of argument, right? So here's the difference of argument. I'm going to call that one alpha. What's the good notation? Alpha and mu. That's the mu, that guy there, minus alpha. That's the guy down there. All right? So mu is the principal argument of w minus w0. And alpha is the principal argument of what? Z minus ZW0. So if you look at this w minus w0 here, represented a vector, what would you say in degree the mu value? By looking at this picture, it's a rough estimate. What is the mu value in degree by looking at this picture? I would agree with that. Definitely not 90 degree, right? Somewhere there in 20 degree or somewhere there. Make sense? What would you say about z minus z0 if the z is over here? Can you see the vector right there? That tiny vector? That's what z minus z0 is, right? What's the argument? 0, right? Okay, always 0, flat and 0. All right, so you know the alpha 0 is 0 there, right? Okay, so that's that. So what would you estimate about the w minus w0? You're looking at this side and here. That's the length of this z minus z0, right? And this is the length of this w minus w0. Would you agree? What is your rough estimate? Would you say this 4 times? 5 times? I think 6 times about right. You can just copy it and would you agree with that? Yeah? This one, length of that one, and compare the length of that one. It seems like 6 times of that one, or 5 times. If that's so, and we have, we're going with the 5 times e to the mu of I mu. Is that right? That's the meaning of this guy here. We didn't take the limit. If you take the limit, what happened to this arrow is that, arrow is almost being this. How did I draw this dotted one? What is the principle? It's the tangent to that horizontal line. This is a horizontal line. Is the image of that horizontal line. If z approaches z naught, you can use Calc 3 to show that it's really the tangent to that this one, right? Okay. That dotted vector is actually, did anybody remember what the dotted vector is a column for? uv was a position, right? How do you get that directional vector? Partial derivative, right? With respect to which variable? You look at it here. Which one varies here? X, right? So therefore it's x and x. That vector is exactly this vector, right? And we estimated with this one, this tangent, this vector here, has roughly size 5. And angle is exactly just, is a slightly different, but you can choose this point in here to a better estimate. But it's roughly just this one. So that's what the derivative is. I just have a right time for the second example, and this is going to puzzle you. All right? The second one is a really interesting one. So here, why not we approach z approaching z0 many different fashion, right? That's what we mean by limit z approaching z naught. So I'm going to look at slightly different direction, like that guy right there. So what does that correspond in here? Which line? It's a vertical line right there, right? So it's going to be w0, and if that's my w in red, and it's going to be w over there, correct? And that's going to be this vector there. Okay? That's going to be w, that's going to be w minus w0. Now I'm calculating this one again, fz minus fz naught. Z minus z naught is roughly, let's estimate modulus. What happened to modulus? quotient of two modulus, right? Looking at this size and that size right there. Don't you think it's just roughly the same length? It's roughly the same length. So would you agree this is also a 5? Right? So that's that angle right there. And there's that angle. So what is that angle? Is I have mu in there. That's its entire angle right there. That's what mu is, right? And minus what angle we're subtracting here? Not 0 this time, because this is pointing upward. Pi over 2, right? It's pi over 2. So that's the estimate. So we got the same length, right? But we're not leaving this one in here. We're subtracting off. Mu is here, but how much we're subtracting off? Pi over 2. So it's got to rotate it back here, right? Rotate it back. Pi over 2. So wouldn't that be just about here? Pi over 2? If you actually play with tangent version, that's exactly pi over 2 right there. So I'm claiming that this rotation backward, and if these w's are very, very close to z0, is actually going back to exactly the same original position. So let me conclude like this. If this w is not long like this, it's very small, then one answer you will get in this one, and the other answer is like this one, but because of this pi over 2 rotation, it's going to put it back right back to where we started. So you get the same result, and both f of z minus f of z0, z minus z0, going to that vector 5 of e to the I mu whatever, versus the other one, f of z, which is in black. That means your z is in horizontal. And if you do that, this one doesn't involve rotating back because your input has no angle, right? So they go to the same thing. That's good because as z approaches z0, however, they go to the same thing. That's what I'm explaining in there. Does that make sense? Yeah. So it turns out this is a good definition. They go to the same thing because of rotating backward map. Algebraically, it's not complicated at all. You just calculate just like you did in a real number, and you get the answer right away. But geometric meaning is like this, and I think it's quite interesting. What the meaning of derivative, if you just force our algebraic formulation from the real number to the complex number, and it has this meaning. All right? Directional derivative, but later clocking backward is involved because of this de Moivre's theorem. And it turns out it's good. It always gives you the same result. I'll stop here.